So with an RL circuit, the way that it behaves is if I plot the current versus time, it has a maximum value of the EMF divided by the resistance, and it goes like this. We have the equation that the current is equal to the max current times 1 minus e to the minus t over tau, where tau is equal to L over R. Okay, so those are the relevant equations from your formula sheet. Now for part A, at t equals 0, what's the voltage drop across the resistor? Well, at t equals 0, we can look at this in two ways. If you notice over here, when t is very small, the slope, delta I over delta t, is large. And that means that the voltage drop across the inductor is going to be large. It's going to be about equal to the EMF of the battery. And if that's the case, then the voltage drop across the resistor will be 0, since the current is basically 0 at that time. Okay, so there are a lot of ways. You could also look at this equation and say, well, if t equals 0 here, then this term becomes 1, and so the current is the EMF over the resistance times 1 minus 1, so the current is equal to 0. So there are a lot of ways to get at that solution. At t equals 0, what's the voltage drop across the inductor? Well, as I mentioned, the voltage drop across the inductor is about equal to the EMF at that time, which is 24 volts. You could also get that from the loop rule, right? Since the voltage drop across the power source is equal to the voltage drop across the resistor plus the voltage drop across the inductor. This is 24, and we already decided that the voltage drop across the resistor is 0, so that means the voltage drop across the inductor has to be 24. Okay, part C, it says, at what time is the voltage drop equal to 25% of its max value? Okay, so the voltage drop across the inductor goes like this. It has a maximum value that's equal to the EMF, and then you multiply by e to the minus t over tau, right? If I were to graph it, delta VL versus time, it would have a maximum value of the EMF, and it would slowly decay. Right? It starts off at a max value and eventually becomes 0 when the current stops changing. Now tau in this case is L over R, and we're given L to be 0.45 henries and the resistance is 24, so this works out to be 0.01875 seconds. Alright, so plugging in then, we have the voltage drop across the inductor is 25% of maximum value, so 0.25 times the max is equal to the max times e to the minus t over tau. Right, so we get 0.25 is equal to e to the minus t over tau. Take the natural log of both sides, and then that gives me t is equal to negative tau times the natural log of 0.25. Now the natural log of 0.25 is going to be negative, so this is negative 0.01875 for tau, and then the natural log of 0.25 is minus 1.386, so it works out to be 0.026 seconds. A little more than 1 decay constant. Part D, at that time, what is the voltage drop across the resistor? Well, if the voltage drop, we already did the loop rule earlier, if the voltage drop across the inductor is 6 volts, we know that the voltage drop across the battery has to equal the voltage drop across the inductor plus the voltage drop across the resistor. And that's 24 all the time. And we're at 6, and we just want to know what's the voltage drop across the resistor. That's 18. Thanks to the loop rule, we can see that. Or if you'd rather, you could calculate I at that time and say the voltage drop across the resistor is IR, and then we could use this equation up here to calculate I at that time, and you could plug everything in to work that out, but you really don't need to make it that complicated.